converging lens is thicker in the middle than it is at the edges. It will bring light together, light from a distant object, together to a focal point. We can see that here. Light from a lamp, which is some way back, is being collected by the lens, and as we pull the lens away, the light is focused, and that's at the focal distance from the lens, at the focal length. It's not focused at exactly a point because the lamp itself is large and therefore the light's not parallel. We can see the same effect with the light from the window. The light from the window is brought together and we get an inverted image projected onto the screen. Here is a schematic diagram showing the action of the lens, focusing the light from a distant object and producing an inverted image. And here's an explanation of how that is done. Diagrams such as this are best done on graph paper because then the scale is easy to measure. We're using here a scale of 1 centimetre on the graph paper to 5 centimetres. We've drawn the principal axis, the line which is down through the middle of the lens, and here we're drawing in the position of the lens. We need to mark the lens, draw in the object and the focal points. A ray of light from the top of the object will go through the centre of the lens where the sides of the lens are parallel, it won't be deviated. Another ray of light drawn parallel to the principal axis will reach the lens and then be turned through the focal point. Where these two rays cross, that will be the position of the image. So we mark in the image at exactly where these two rays cross. It's inverted and it's real. It could be projected onto a screen. And again, a reminder of the final diagram. A second function of a converging lens is to act as a magnifying glass. As you pull the lens away from an object you're looking at, it gradually gets larger. But there's a point as you pull it further and further away in which the image gets larger and larger and then becomes out of focus. We're going to try and show how this happens on a diagram. Again, we draw the principal axis in, draw the lens in, and mark the edges of the lens so that we know that is the lens and not the object. Now, we mark in the focal points, and again we're using a scale here of 1 to 5. 1 centimetre on the graph paper to 5 centimetres in actual fact. So the focal point is 15 centimetres away from the lens. You'll notice it's 3 divisions on the graph paper. Draw the object in 10 centimetres from the lens, that's 2 centimetres on the graph paper. Again, we draw a ray of light parallel to the principal axis, and that is going to be turned through to the focal point. A ray of light going through the centre of the lens will not be deviated, and these two rays of light you can see are diverging. They're not crossing, unless of course we draw them back. Now the light doesn't really come from here, but if your eye is placed so that you see the light coming from the lens, then that's where the image seems to be. And so this image is a virtual one. It seems to be there, but it is not really there. In this finished diagram, you can see that the eye on the right-hand side is looking up towards the light. That light seems to be coming from the purple image, which is a virtual image much magnified. If the object is placed at the focal distance from the lens, then the light as it goes through the lens is parallel. It goes into the eye and the eye lens focuses it. This is a very comfortable position for the eye. It's called normal adjustment, and the eye is focusing parallel light as if it was from a distant object.